exciting legislation with Western Australia. He's going to continue talking about atomic clocks this morning.
Thanks very much. So we've talked in the last two lectures about noise and modulation, fluctuations, and then we moved on to talk about locking lasers to macroscopic resonators where we could have lots and lots of signal, but we had reasonably high sensitivity to environmental changes. And so today what I want to talk about is an atomic clock, which is basically locking lasers. Principally we're going to talk about optical atomic clocks, so locking a laser to some sort of transition in atoms or ions, which has the disadvantage of less signal, but the advantage that in principle, well, let's say with care, one can have vastly less sensitivity to environmental changes. So the outline of the talk is essentially to look at why do we build these atomic clocks, what performance can we really aim to achieve, and talk about the fundamental bases to these clocks and the limits, and finally to look at some of the different solutions that people have used to actually come up with that. So in order to motivate the discussion, what I wanted to do is turn to the most, let's say, one of the most fundamentally interesting measurements you could attempt to make, which is to try and detect evidence that either there's something wrong with the current conception of physics, or maybe you prefer to think of it as searching for new physics, which essentially reflects the fact that we all understand that there are fundamental incompatibilities between relativity and quantum mechanics and gravity, which it's been a long hoped for dream of theoretical physics to find this so-called theory of quantum gravity in the middle of this pie chart here that unifies all of physics. And some of the theories which, let's say, some sort of speculations about the types of theories which actually unify all of those physical laws predict that some of the hypotheses or the assumptions that we make are not in fact valid, and they might be things like assuming that the fundamental constants are indeed constant is our current assumption, but perhaps there's a problem with that, in that if we could find evidence that those fundamental constants are changing, these might be hints to the types of theories that provide unification. So people have been doing this for a long time, and typically what they tend to do is look for changes in the values of constants which have no units, such as this fine structure constant, which is the ratio of the square of the charge of the electron over Planck's constant and the speed of light. And there are two ways to go about looking for changes in the values of these dimension-free constants. One way is to make astronomical observations, and that's what I'm going to tell you about to start with. The second way is to use different types of atomic clocks, compare the frequencies that are output from those atomic clocks to look for these changes. And there's been really the strongest, some people who are playing a very strong part here were at the University of New South Wales, and some nice resonance the fact that you're in Australia at the moment. So essentially the goal is to make use of observations of quasars in the far distant, and this quasar light passes through clouds of relatively cold vapour on the way to the telescope that's over here. And when you look in the spectrum of these quasar light, you see these absorption dips which correspond to absorption from these clouds in between. And if one looks at where those lines are, there's overall shifts of those lines due to the relative velocities of the Earth and those clouds. But on top of that, there are some tentative evidence that all of the lines are shifted in such a way that suggests that there might have been a change in the value of the fine structure constant at that far distant location. And I should mention that this is relatively controversial, but nonetheless the publications are appearing, the claims and counterclaims are appearing in prestigious journals. So the first one is one from the University of New South Wales. They did a search looking at these absorption lines, and they claimed, in fact, that there was a change in the value of the fine structure constant, a fractional change to the level of half a part in 10 to the 5. And people have gone on to look for other types of changes in these fundamental constants, like, for example, the change in the ratio of the electron to the proton mass, and seen similar sort of magnitude changes. Of course, all of these things would be inconsistent with the standard model of particle physics, where we hold these types of constants to remain indeed constant, as well. call them constants, right? So this is sort of an interesting thing, that something like, that these astronomical observations are predicting something like nearly a part in 10 to the 5 change over something like 10 billion years. And it's also inconsistent with an observation in regard to a natural nuclear reactor that's in Africa, which seems to suggest that the fine structure constant has not changed at all over something like 1 billion years. And so what's of interest is to do modern measurements now to see whether we can detect changes in these fundamental constants. So with much higher precision than the astronomical measurements, but also over much shorter timescales. So if you were to make a linear approximation, and there's no reason, as I understand it, to not do that, you might be interested in looking, if this is the change over 10 billion years, you might be interested in looking at parts in 10 to the 15 change per year to be at an interesting level, and hopefully somewhat better than that. So here are the best 2 results of using atomic clocks to search for these types of changes. And so one was done in Germany, and this one over here is from Boulder, and well, in fact, a whole contribution of a bunch of people at Boulder, as well as work in Germany and France. And essentially by comparisons of ratios of clock frequencies, so the mercury ion to the cesium clock, or the hydrogen, a particular hydrogen transition against cesium, you can basically put various boundaries on what the fractional change in alpha must be, that's along that axis, versus the fractional change in the cesium magnetic moment with respect to the Ball magneton, I think was this axis here in this case. And basically they can home into a region which is consistent with all of these ratios, or the observed amount that these ratios have changed, which is essentially noise limited. And you can see that the ellipse is consistent with 0 change of both of those parameters. The central of the ellipse is off 0, it's within the error bars of 0. So obviously what would be really, really nice is to improve the performance of the clocks that contribute to this sort of diagram by another factor of 10 or 100, and then we can really see whether we can make a modern measurement which predicts whether these constants are in fact constant. So I hope that motivates you for building atomic clocks which have a performance better than parts in 10 to the 15 accuracy better. Alright, so what sorts of things do we need in a clock? This is a similar slide to that which we saw yesterday, but rewritten in the sense of quantum particles. So what we'd really like is narrow resonances. And as we'll see in the next couple of slides, if you want to have a narrow resonance to lock to, that essentially means that the interaction between your probing source, which is going to be a laser in our case, and the atoms, needs to be long, because that sets the ultimate limit as a Fourier transform limit, so you want a long interaction time. And if you need a long interaction time, then that tends to mean that the upper state of this transition of probing needs to last for at least that long. And so what we're looking for is long-lived levels in atoms. So that's going to set which particular atoms are most useful to us. On top of that, you want the atoms or ions to hang around inside the laser beam for at least that amount of time, otherwise the interaction is not that long. So you tend to be interested in slow-moving atoms or ions, or trapped atoms or ions as well. And of course the thing we want to do is choose atoms which are not going to be extremely sensitive to changes in the environment, essentially. On top of that, you'd also like to have lots of particles to interact with, so you've got great signals noise. So I want to present a little thought experiment to you. I want you to imagine that we've got like a box with a collection of atoms in here, n atoms sitting in my box. And we're going to set up an experiment where I'm going to throw n over 2, half the number of atoms worth of photons at my box. And imagine that most of these atoms are starting from the ground state, and the laser that we're throwing at is tuned to the transition between the only 2 states available in this 2-level atom. And we've set the experiment up so that all the photons essentially get absorbed in there, and all of the atoms are equally likely to absorb the photons. So a very idealised experiment. And I want you to think about what's the state after I've thrown that pulse of photons at it. I mean, is this the right picture after I've thrown my n over 2 photons? Do we have half of the atoms excited and the other half unexcited? Is that the right picture? Or do we have, if you're worried about whether that's happened, also think further, like that we've thrown another n over 2 photons, and what's going to happen after I do that? Or is the better picture some picture like this, where we imagine that all of that happens in the box? After my first half the photons photons are thrown in my box are in a mixture of the ground state and the excited state. And I think, a priori, without thinking about it very long, I don't think it's very obvious. But, atomic clocks wouldn't work unless this was the correct picture to use here. We're going to suggest that as these photons come in, we're going to get an equal excitation on each atom so that it's in that mixture, superposition between the ground and the excited state. And for those of you that are familiar with this sort of density matrix theory, there's a few equations on my slides, but what I want to do is present a bunch of graphics that try and make it plausible what's the behaviour of this interaction between the atomic system and the photon system without needing to follow through any of these equations. So let me show you a movie here. This is a movie of my atoms, and here's my sort of, completely symmetric ground state and some sort of excited state in the atom, like for some sort of arbitrary atom here. And I say that I'm showing you a movie because, of course, these ground state and excited state are supposed to be eigenstates of the Hamiltonian, so they're time invariant things that just sit here, don't do anything. And what I'd like to show you is, like, in the state after I've thrown my n over 2 photons at my n atoms, what is it going to look like? And it actually ends up looking, here's my little diagram, it's going to look something like that. So it's a 50% superposition between those two wave functions of the ground and the excited state. So in this picture here, there's no input, external input coming into the system from the laser beam. There's no change in the occupation of the ground state and the excited state. It's just a 50% superposition between those two states. And because the two of them are evolving at a different rate in time, because they have a different energy, we're going to see this apparent oscillation in the wave function superposition due to the interference of those two. And of course, the frequency that this thing's bouncing up and down is at exactly the energy difference of those two states. So you might like to think of it as it looks awfully like a little antenna here that's oscillating backwards and forwards at the difference frequency. It's almost like a clock in the system, which is really, really nice. And that's really the basis by which one of the big techniques for atomic clocks is going to work. We're going to use this 50% superposition. For those of you who like the density matrix picture, in some sense this is the coherence or the dipole moment of the atom that's flopping backwards and forwards due to this beating between those two wave functions. Okay, well, as I said, that's just the 50% superposition. There's no external laser force in that system driving, so there's no variation of those two populations. What I want to show you in this picture is something which superficially looks similar, but it's quite different. What I'm suggesting here is now I'm going to push the atom with my external laser, so I'm going to drive it from the ground state, which we're starting here, into the excited state. And so what we see is a picture like this. So we see the laser start to induce some sort of oscillation, and then the system actually ends up in the excited state. And if we continue driving the system, then it's driven back down to the ground state again. And here we have one of the techniques by which people build atomic clocks, which is that they make use of this flopping between the ground state and the excited state, which is called Rabi flopping. And the rate that this occurs, and also, in fact, the fraction of the atom which ends up in the excited state depends on the detuning between the laser and the atomic transition. And so if we set the system up so that we give it a burst of external energy to drive, which we've arranged in order to completely invert the population, for example, if we get a change in the frequency of our external laser clock with respect to our atomic clock, then we're not going to end up with driving it all to the excited state, for example. So we can basically plot out a curve which corresponds to a detuning between our external laser. So we give the system a burst for a well-defined amount of time from our external laser, and then we measure the population at the end of that burst of energy and see whether it's ended up fully in the excited state. Well, that's one way. The more common way that we see, the more common type of interrogation technique is not the Rabi technique that I just showed you there, where we're forcing the system to make a flop between the excited state and the ground state, but to do something called the Ramsey technique. And the Ramsey technique is an intrinsically pulsed technique where we are going to basically have an external clock, which is basically a laser connected to one of these cavities that we talked about yesterday, so a stabilised laser which defines one sort of timescale, and our quantum system over here. And what we're going to do is do a sequential process in order to interact. So let's imagine we take our laser and we fire it into the system, and we start causing that sort of oscillation. But what we do is we stop at some point. We stop the interaction, and then we just let that atomic system freely evolve in that 50% superposition state. Now, of course, at some point, I can turn my laser back on, connect it back up to this quantum system. And what the system's going to do depends on whether my laser is in phase with where that atomic oscillator has got to. So if it's still in phase, then we're going to continue driving that atomic system up into the excited state. And if it's not in phase with the atomic system, it's going to drive it back down again. So now we have a system which is very sensitive to what's been going on in the phase difference between my laser clock and the atomic clock in that time between the times where I drove the interaction. So that's quite a different approach, because in this case I stop perturbing the atom while it's freely evolving. And that's really something that we quite like, because it means I'm disconnected from the environment, and it's much more the free atom which we're hoping for in order to define some quantum absorber. It's less connected with the environment. And what's important in this case is really the time between the two interactions, and the interactions themselves are nowhere near as important, so one gets a lot bigger degree of freedom to play around with the interactions and more efficiently. It turns out you can more efficiently couple more atoms if you use this Ramsey approach rather than Rabi-Flopping approach to the clock. Nonetheless, you can plot out something that looks like this. So in this graph here, what I'm plotting here is the fraction of the population that I've driven to the excited state. And this is some sort of arbitrary frequency detuning, but well, it's actually hertz. And I imagine that I've got a 1 second pulse coming into this atomic population, and we see some sort of picture like this. So when I'm in resonance with those atoms, I'm very efficient at driving them up into the excited state. And as that detuning falls away, and the width of this sort of frequency feature is something like 1 hertz, which is not so different to my 1 second duration. This is the Ramsey sort of configuration, so this is the case where I drive the system, then let it freely evolve, and then drive the system again afterwards. And in this case here, I've set the time between the two interactions to be 1 second. And in terms of building a clock, this sort of feature or this sort of feature is almost equally useful, because it defines resonances that are something like 1 hertz wide. Of course, all this is built, let's not forget, but all this is built on the fact that throughout the entire interaction, or throughout this entire 1 second period, I've got a strong interaction between my laser and my quantum absorber. And in addition, that the system doesn't decay from that excited state, so it has a lifetime of about 1 second. Well, if we're in that sort of dream world where those two things are true, then how well could you potentially do? And you can write down some sort of back-of-the-envelope expression like this for calculating the square root alpha variance for the system. So if we have a 1 hertz wide resonance, then the effective Q defined by this atomic resonance is something like 3 times 10 to the 14, and if we have something like 10,000 to a million atoms inside the beam, which might be a typical number trapped in one of these lattices that we'll talk about in a few minutes, then you can imagine you could get an Allen variance of something like 10 to the minus 17 at 1 second. The square root Allen variance is minus 17. Well, nobody's yet reached that level, and we'll talk a little bit about why that's the case. Although the quantum, and we'll talk about some specific cases of that as well. So the first thing I want to tell you about is a very simple clock based on like a beam clock apparatus, which is something that people have been building for about 30 to 40 years, and it started off in the microwave domain. I'm going to tell you about an optical version because I think it's a nice introduction to seeing in reality how these atoms work, and then later on we'll talk about one of these neutral lattice clocks as well, the work that's going on. Well, there might be a question as to what elements does one choose to build one of these atomic clocks. And you might have heard of things like cesium and rubidium clocks used to be the elements of choice for micro clocks, and that's because all of this group 1 has splittings in the ground state that correspond to useful microwave transitions. But as we move into this optical domain, you might have a question in your head as to how we go about choosing the elements for that class. And so what we're looking for is an element which has a long-lived transition, and as it will turn out, we need to do some laser cooling on these elements as well. So what we tend to look for is an element which has a very fast transition in order that we can do laser cooling, and also needs a very slow transition with a lifetime of a second or longer in order to provide our optical frequency reference. And it turns out that all of these 2 electron elements and these things that are over here, and the terbium down here, which are effectively 2 electron elements, are really the right choices to use. They have basically a strong resonance transition when we're interacting with one of the electrons, much like all of the laser-cooled elements in group 1, but they also have a spin-flip transition, an intercombination transition, which is really long-lived because it's either partially or fully forbidden, so it can have lifetimes from seconds to years on that type of transition. So let's have a look at one example of an optical beam clock, which is one that we built in my lab based on transition in calcium, which is one of those group 2 elements, and maybe that'll put some of the abstractions into the concrete here. So what are the relevant energy levels of this calcium material? So the convenient thing is the ground stays down here. It's got a very strong transition, which is shared with all the others, as we'll see with strontium later on. It's a resonance transition. In this case, it happens to be the blue part of the spectrum, 423 nanometers. And it's got a very short lifetime, so we can use that to do laser cooling and detection of the state of the atom, whether it's in the ground state, or whether it's ended up in this metastable level over here, which has a lifetime of half a millisecond. It turns out there's another transition just below here that's also in this triplet set over here that has a lifetime that's immeasurably long. So in principle, one can build the clock based on this bottom transition here if the atoms were trapped in an appropriate lattice, which is a goal for us for the future. So the advantage of using this transition also is that this has a very low magnetic sensitivity, which is something you want in a clock. So how does this thing work, and how does this connect to the pictures, the wave functions that I was showing you in the very beginning? Well, essentially we have a strong beam of calcium that's collimated down the bottom just by some simple slits, and we use one of these blue beams to detect the state of the calcium. So this is a very common thing that's also true for modern clocks as well, that you use the strong transition to detect the presence of calcium atoms in the ground state. This happens to be at this particular point here. And in fact, as we scan the frequency of this laser, we see all of the natural isotope components of a real calcium mixture. You'll see that the transition width here is something like 50 megahertz wide. So no one would build a clock on that. That 50 megahertz wide essentially comes because of the Doppler broadening of that the residual Doppler broadening of the fact that the beam has actually got some divergence. Okay, well let's do something more interesting. Let's drive the system with the red laser at this lower point here. And as we scan the frequency of this red laser and leave the blue laser locked onto the central frequency of that fast transition, what we see is a little dip in the resonance that's something like 6 megahertz wide. So that's in the frequency of this red laser. And of course what's happening is this red laser is coming to resonance with that slow transition, and we're driving the atoms up into that metastable level, and so they apparently disappear as far as this blue laser is concerned up here. So you might think to build a clock on this, but once again, this is 6 megahertz wide, so that's not remotely interesting really in terms of precision. So how do we do better than that? And so some of you might have heard of a concept called saturated absorption before, where basically we retro-reflect this laser beam. And then so for one class of atoms, they basically see both of these laser beams, and that's the class that's going directly vertically. All of the other classes which are leaning to the left or right that have some divergence with this beam are only going to come into resonance with one of these atomic beams as the frequencies tune. So now once again I can plot for this retro-reflected configuration, and what one sees in the middle of this resonance is a little upward dip because those atoms there have actually interacted with both of the beams. And so we see a little tiny dip which is substantially narrower. In fact, it's 215 kilohertz wide rather than that 6 megahertz, because this little weak blip is essentially those atoms which are the zero transverse velocity class. So this is sort of starting to get interesting, except we gave away all of our signal to noise. Well, where does the fancy quantum stuff come into it? Well, if we, instead of just retro-reflecting here, if we set up pairs of co-propagating beams, then we've effectively set up that Ramsey configuration between, for example, this beam here and this beam here is talking to one class of Doppler-free atoms, and we can set up a beat between those two with the next two. So we're essentially writing the coherence of the laser into the atomic population, and then we're reading it out with the second interaction that's occurring slightly later. And if we do that, what we see is we see some interference fringes in the middle of this curve that essentially reflects the time of flight between these various beams. And so if you sit down and do a quick calculation that the thermal velocity for this system is something like 670 metres per second, and we make the beams 5 millimetres apart, we see some little fringes that are 33 kilohertz wide. So that's a simple continuous approach to actually reading out this beam, and it's the basis to the clock. And as we'll see with the lattice clocks, essentially instead of separating these interactions in space and using the velocity of the atoms to effectively convert that to time, we just basically hit the trapped atoms with a time separation. But essentially, let's say the principle is exactly the same. So we're writing some coherence into the system and then converting that coherence into a population difference with the second set of beams. Let's not concentrate on that too much. And so if you basically sit down and do a theoretical calculation as to what you expect, you see something like this, and if you do the experimental measurement, you see something like this. And so you feel vindicated because everything looks about right. It's about 3 times less less efficient than you would hope, but well, let's just jump this because we're going to run out of time. So about that. Okay, so one little trick we do is then to actually convert this little resonant signal that we can see into something that can steer our laser. We modulate our laser backwards and forwards like we talked about yesterday in the Poundry to Hall system where we're locking the laser to a cavity, but now we're using the atomic resonance to actually be effectively the resonant structure, and we modulate our laser backwards and forwards over that, and we can generate a nice error signal like we saw yesterday for locking the lasers to the cavity, but now we're locking lasers to the atoms. And if one looks at the signal to noise of our situation, we get something like parts in 10 to the 13 Allen variance, which turns out to be better than any commercial atomic clock that you can buy, but certainly not as good as the laboratory. So if we compare our optical beam clock against something like a hydrogen maser, what we see is just a white noise signal, which has the corresponding 1 on the square root of integration time dependence over here, and basically we're just seeing the hydrogen maser, which is the best commercial clock you can buy noise for. Now if we compare it against an extremely good cryogenic clock that we've got in our laboratory, we start to actually see the fluctuations which are associated with this calcium beam clock, which is slightly better than parts in 10 to the 13 in 1 second, so something like 2 to 3 times better than a hydrogen maser. And so here's the summary plot that I've been using frequently. I put the calcium clock on there, so this hot calcium beam is a little bit better in the short term than the best commercial source you can buy, and that starts to show you why people are interested in moving to optics, because a very simple continuous beam-based optical frequency standard can actually beat the commercial standards. Of course, we're still something like 30 to 100 times worse than the best standards based on ion traps and on cold calcium inside. So this is cold, freely expanding calcium, or alternatively strontium, which has been trapped in the lattice. So let's now have a look at the fancier ones. Let's have a look at the neutral atoms which have been trapped inside an optical lattice and understand how those types of systems work and see the performance of those. So this is a very busy slide, which is essentially a summary of all elements which have been proposed as optical frequency standards, and essentially the various cooling transitions as well as the clock transitions. And you can see the one that we're going to study in the next few slides, which is strontium. The particular transition they use can have a lifetime of the order of hundreds of seconds, or equivalently a frequency width of a millihertz or so, which is a really interesting narrow transition, and it's going to be a real challenge building a clock laser that's narrow enough to actually interact with that. It turns out that, you know, when they actually try and load these lattices, there's a whole bunch of complexity that involves 7 or 8 lasers in order to load the lattices efficiently and then interrogate the atoms. Unfortunately, we don't have time to talk about any of those things. What I do want to talk to you is about this lattice and the remarkable breakthroughs that have occurred that basically means that we can actually use these optical lattices to trap atoms and build a sensible atomic clock, something that 10 years ago was thought to be impossible. But thanks to this fellow, Katori from Japan, basically suggested a way in which this could work, and it's sort of been termed these days in the literature as the magic lattice sort of technique. So you might have heard some of this already during the last 3 weeks, so I'll just cover it relatively quickly. Let's imagine we've got a collection of atoms which we're trapping in a 3-dimensional optical lattice, so we've set up 6 laser beams to set up a modulated intensity lattice in 3-dimensional space, and we've tuned that lattice light so that it's not in close resonance with any of the atomic transitions in the atom that we're interested in trapping in there. And the reason that we do that is that if it was in resonance with the atom, then we drive spontaneous emission which would heat the atoms and also destroy the coherence of the system. So it's a very farly tuned optical lattice. And the idea of it is that if the lattice is red detuned with respect to the nearest resonance of the atoms, then what happens is the atoms will feel their ground state energy level to be drawn downwards when they move into the brighter areas of the beam, so they're drawn to the brighter areas of the lattice. If the lattice, on the other hand, is blue detuned with respect to the nearest resonance, then the atoms would feel their energy levels lifted in the bright parts of the beam, and so therefore they're pushed away from the bright parts and drawn to the dark parts. So the problem with these lattices has always been that people thought in order to exert a force on the atom and hold it in some particular place in the laboratory so we can have a very long interactions on it, the challenge was that that would shift all of the atomic levels and therefore destroy your ability to actually make a clock. You could never control the lattice parameters well enough so that it didn't disturb the resonances and damage the ability to build a clock upon it. The breakthrough was really from this work in 2001 by Katori, where he suggested, well, real atoms don't have 2 levels, they actually have lots and lots of levels. And so if we're very careful with our choice of wavelength for the lattice, it's possible that we can couple the ground state to some set of transitions over here and couple the clock state that forms the top end of that clock. So our clock system is between this ground state and this lower transition of the triplet here, so we're building a clock between these 2 levels. And if our lattice light, which corresponds to none of the transitions in this system, connects both of those states to another family of transitions, it's possible that we can do something like this. So in the particular case of strontium, it's at 813 nanometers, this transition. And so it connects this ground state to nothing here and this excited state to here. But predominantly the interaction is via the detune this transition and to this 3s1 transition here. And what we see is that shifts both the clock and the ground state by exactly the same amount for that particular wavelength. And so when we make a measurement between these 2 levels, we notice no effect of the lattice on the clock transition itself. And that gives us a great independence of polarization of the lattice and the intensity of the lattice. So because the clock transition stretches between these 2 levels and we chose the correct transition here, there is no, to first order, no shift in the actual clock transition, which means it's realistic to build a clock based on it. Here's another way to show the same thing. What I'm here is plotting the shift in the upper clock level and the lower clock level as a function of the wavelength of the trap, and we find that at some particular wavelength, which is 813 nanometers in the strontium's case, those 2 things coincide. So there is no sensitivity to intensity. So whether the atom's in the excited state or the ground state, it feels exactly the same shift from the lattice, which means that also we don't disturb the coherence of atoms trapped within the lattice as well. And here's a bunch of experimental measurements of the same thing in much greater detail, so we can see the differential light shift between the upper and lower clock state as a function of the wavelength of our lattice, passes through a zero here. Alternatively, you can think about the light shift to these levels, and if you tune it to the right place, there's no intensity dependence on the clock laser. So that's a very, very powerful technique because it means that we can trap our atoms in the lattice, have an indefinitely long interaction time, and the presence of the lattice itself doesn't disturb the atoms to any great extent. All right, so what I wanted to do is go back to this slide where we considered the various things we need and show you the sort of best results that have been achieved so far. So I asked for a narrow resonance, and in fact, if you go and measure the atoms in one of these lattices, these are strontium atoms that work at Gila, trapped in the lattice, then you can really see a resonance that's something like 2 Hertz wide. And so that seems all good. I wanted something like a 1 Hertz wide resonance, so that seems all good. We want lots of particles, and it turns out that it's relatively easy to get something like 10,000 atoms into a lattice. You go and think about environmental sensitivities, and people worry about an awful lot, including things like, for example, what's here called the black body radiation, which is the fact that the chamber, the vacuum system that contains all of this actually has finite temperature walls, and there's black body radiation emitted from those walls, and that actually interacts with the atoms and shifts it through these same sort of, essentially like making a radiation environment that shifts all the levels as well, so something called the black body radiation. And indeed, things like the gravitational redshift has all become relevant. So the summary to all of that is something like the environmental parameters are only causing something like parts in 10 to the 16 shifts, or 0.1 of a hertz. So that's all looking really nice, and so it seems like the real numbers suggest that 2 by 10 to the minus 17 is a plausible Allen variance to aim for. What have people actually achieved? So these are the best results of very recent, just been published in the last month, and we see something like an Allen variance. The best people have achieved is something like 2 or 3 parts in 10 to the 15, not 2 parts in 10 to the 17, like 100 times worse than you would hope. So why is that? Well, actually we already know the answer to that, because it turns out that what we saw yesterday when we had a long chat about thermal noise in cavities, which are causing fluctuations in the positions of the mirror surfaces because of essentially fundamental grounding motion is causing noise in the laser which is locked to it. And it turns out that the noise of the probing laser is translated into noise in the output of our atomic clock. And the reason why that happens is essentially because we're using this Ramsey configuration for the interrogation. Because we sample the atoms at 2 different times, that periodic interrogation essentially upconverts low frequency noise in our probing oscillator into the bandwidth where it's actually of interest. And this combines with the fact that when we make the probing of the atoms, there's a secondary problem, which is that each time we probe the atoms, we tend to destroy their state and they escape from the lattice. And so each time we want to compare our laser against the atoms, we need to reload the lattice, which involves a whole bunch of laser cooling and quantum preparation steps. And that actually consumes more than 90% of the time. So only 10% of the time are we actually making the comparison, and the other 90% of the time we're just preparing. And when we're in that configuration, where we have that very, very small duty cycle, the problem is that we end up directly converting the noise in our probing laser into the output of the clock. So what I wanted to say was to finish that really atomic clocks, as they stand at the moment, are really poised at an interesting time, because they certainly have the potential for parts in 10 to the 17. There's no showstopper there on any really serious ground. The problem is our probing oscillators just are not good enough in order to fully exploit the potential of the atom. So we really need to push that the locking of lasers to cavities and improving the qualities of the cavities to which they're locked in order to fully exploit the potential of the quantum absorbers. Nonetheless, there has been work with trapped ions in RF traps that have demonstrated accuracies by integrating up for relatively long times, at the order of 1,000 seconds, So they could show accuracy of 2 parts in 10 to the 17. So the other thing I wanted to point out, that when we easily say these numbers of stabilities or accuracies at that level, what's an example of how remarkably small these numbers are is that the shift due to general relativity corresponds to parts in 10 to the 16 per metre when you're on the surface of the Earth. So if you want to compare 2 clocks, you really need to know their altitude on the surface of the Earth, or essentially their relationship with the point of equal gravitational potential to within centimetres if you want to start to make comparisons at this sort of accuracy. And of course, general relativity is a pretty small effect. Well, my finishing remark is really that there's something that's long hoped for, and if people can overcome this problem with the probing oscillator, so it's a narrow and more monochromatic interrogation, then there's something that people are really interested in, which is to essentially produce by some means, which is not entirely clear yet, a cooperation between all of the atoms, so that they respond to the external interrogation in a manner where they know what each other are doing. So instead of being essentially a bunch of independent entities, you want them to essentially know what all of the other atoms are doing. So that all the formulas that I presented to you today assumes that every atom is acting independently of the others, and they settle the noise flaws. But potentially, if you can produce a state that essentially that all of the atoms can share some quantum information, it's possible to do substantially better again. But of course, until we solve the problem with the interrogating oscillator, there's little point in pushing it in this direction. So on that, I'll finish. Yeah.
Thank you very much for a really interesting talk. We have time for a couple of questions. Yep.
Is there actually, like, have the oscillators reached any fundamental physical limit, or is there actually room to push the quality of your probing oscillators?
They're all at the limit. All the best probing oscillators are at the fundamental thermal limit, so not at a quantum limit, but the one imposed by Brownian noise motion of the mirrors. So that corresponds to something like parts in 10 to the 15.
So are there any schemes to improve those, or?
So you could cool your, one way to get rid of that is just cool your oscillator, cool your cavity down to 4 degrees Kelvin. So you can mount the cavity inside some sort of dewar, for example. Then you introduce problems with vibration, which is why I was talking yesterday about all of these schemes in order to remove all the vibration sensitivity. So one brute force approach is let's just cool down the cavity to in a dilution fridge or something. If you had $1 million, let's go. No, we'll just cool it with a dilution fridge, and you solve this problem so that you can push to parts in 10 to 17. Maybe you can do something smarter, because it turns out that this thermal noise is all driven by dissipation of the acoustic dissipation in the cavity. So if you can build your cavity out of other materials which have less acoustic dissipation than ULE, which is what everybody's building, some low thermal expansion ceramic, then you can get over there.
Any further? Yep.
You're talking about reasons why these clocks are not as accurate as you want. Do you ever run into the problem of purity of your samples, of your...
Of the atoms,
you're
saying?
Yeah. Is that an issue at all? Or?
Well, it tends to be to first order, because your laser picks out one particular thing, you only talk to that in any case. But there are indeed collision shifts with background gas radiation that you are worried about. And so you do need to worry that your vacuum is very good, and you're also worried about collisions with background gas atoms destroying the coherence of the atoms within the lattice. So certainly you're pushing vacuum technology to high degrees. In our particular case, as you saw, each of the isotopes has a different resonant frequency, so you only end up talking one. So you're only worried about the sort of background collision of things.
Any other questions? If not, let's thank... Oh, you got a question?
I'm sure you mentioned at the beginning of the talk. So with this kind of system, what you need that limit of 2 to the 2 times 10 to the minus 17 to be able to detect the change in based on the astronomical observations, I guess, check that.
Indeed, that would be the, well, no one really knows if there's anything going on, because it could be that all of this evolution in the constants occurred in the early part of the universe and it's stopped now. But I guess the goal is to do, let's say 100 times better than the moment As I understand it, string theory doesn't predict the particular level of drifting, and the constants just suggest it will be there. So one needs to struggle for every little bit of precision you can get in order to keep ruling things out.
Okay. With that, let's thank Andre again.